Okay, picture this. You've got a single exam paper sitting right there under a stark spotlight. 9 out of 10 physics students taking their Cambridge A-level exams end up losing top grades. And it's actually not because they don't know the math. It's because of one quiet little mistake. So in today's explainer, we're going to expose that exact error by totally mastering the concept of repeating order and long-range structure. We are definitely not just looking at flat, boring textbook definitions here. We're going to visualize the physics right down at the atomic level, and I'll show you exactly how examiners connect those hidden mechanisms to the macroscopic world we see every day. Let's make the invisible visible. Right, imagine this exact text circled in glowing, aggressive red ink on your paper. This is what we like to call the definition trap. And man, it is a cold, hard killer of marks. Here's how it happens. A student is asked why a material behaves a certain way, and they just write something like, "It is an insulator. It has high resistance." Boom. 0 marks. No way around it. Why? Well, because just stating superficial labels without actually linking them to the atomic arrangement is a fatal error in these exams. You're just stating a property, you're not explaining the physics. Examiners don't want you to just memorize labels. They want to know exactly why it has high resistance. And that why literally always lives in the microscopic structure. So if you leave out the connection between the atomic arrangement and the outside behavior, you've walked right into the trap. You can really see the stark contrast here. Over on the left, we've got the flawed answers. Honestly, this is where most students live. They write these unplanned lists of isolated facts, kind of just crossing their fingers and hoping one of them randomly hits the mark scheme. They focus entirely on the macroscopic result with super vague wording. But look at the top band answers on the right. This is exactly what we are aiming for. Top-tier candidates use disciplined prose. They present a logical, connected chain of thought that links a microscopic cause straight to a macroscopic effect. They actually show their method. Examiners are actively looking for this kind of structured reasoning to award method marks. It's not just about guessing the final word. It's about proving you truly understand the journey from the inside of the material to the outside. Okay, so let's lay down the foundation. What exactly is repeating order and long-range structure? Well, it's this foundational idea that the macroscopic behavior of a solid, how it stretches, how it conducts electricity, how it handles heat, can be interpreted directly from what is happening internally at the atomic or carrier level. This is a massive shift in how we learn physics. We literally have to stop looking at a solid object as just a dumb block of material. The physical effects we see on the outside, they always begin with the repeating crystal arrangement on the inside. Whether we're talking about the packing of the atoms, the direction of the bonding, or how it tolerates defects, the long-range structure is the invisible boss that dictates all the macroscopic rules. So to make sure you absolutely never fall into that definition trap, let's break down the ultimate high-mark answer framework. It's a 4-step sequence, and it is practically bulletproof in exams. Step 1, identify the structure or process. Step 2, explain the microscopic mechanism. Ask yourself, why does this happen? Step 3, state the observable macroscopic effect. Basically, what happens? And finally, step 4, connect that consequence to a real-world application. Honestly, if you can explain these 4 stages in order, you are proving to the examiner that you understand the topic deeply enough to completely ace both short and extended reasoning questions. It totally forces you to build a bridge from those invisible atoms all the way to the real world. Let's see exactly how this framework builds in a real exam scenario with this full-screen visual. Take a look at the case study on dielectric polarization down there. Look closely at that microscopic box. We are visualizing an external electric field being applied to a material. See those positive and negative charges inside the dielectric? Well, unlike in a standard conductor, they aren't free to just flow away. Instead, what we see is bound charge displacement. The charges just shift slightly from their equilibrium. This right here is the exact step-by-step internal physics happening within the long-range structure of the material. Let's magnify that microscopic mechanism for a second so it is crystal clear. When you apply an external electric field to a dielectric material, you have to explicitly state in your answer that the charges inside cannot move freely. That is your structural constraint. Because of that constraint, the charges are forced to just shift slightly from their natural resting state, their equilibrium. And here is the absolutely crucial point. That tiny microscopic shift across the repeating order of the solid is exactly what creates polarization. By writing out these specific bullet points in your exam, you're locking in those method marks. You are clearly explaining the why before you ever even mention the macroscopic what. Now, following this exact process forward on our visual, let's take that microscopic polarization and follow the arrow directly to the macroscopic effect, enhanced capacitance. This is where the magic happens, right? Because those microscopic charges shifted and altered the internal electric field, the real-world macroscopic result is that the capacitor can now store way more energy. It brilliantly illustrates the entire micro to macro chain. You didn't just lazily write, it's a dielectric so it increases capacitance. No, you proved exactly how the repeating order and bound charge displacement made that real-world application possible. This is for sure the disciplined chain of thought any examiner wants to see. Okay, here is a top-tier examiner secret. This is really what separates the A candidates from the A-star candidates. Once you've explained that perfect microscopic to macroscopic chain, you absolutely need to account for external constraints. High-tier answers always mention the limiting factors. Look closely at literally any physical system. The effect is never infinite, right? You must state how external factors like temperature, the purity of the material, or the maximum field strength will limit these microscopic effects. For instance, if the temperature gets too high, the repeating order vibrates violently and actually disrupts the polarization. Adding just a single sentence about these physical limitations shows the examiner that you understand these crystal structures exist in the messy real world, and that secures you those final, super elusive marks. All right, let's make this a bit interactive. I'm going to give you a brand new, totally flawed scenario and a 10-second challenge. Imagine a ticking clock. A student is asked how a semiconductor wafer conducts electricity when heated. The student writes, thermal energy is applied so the semiconductor becomes a conductor and current flows. You've got 10 seconds. Can you spot the missing microscopic link in that explanation? Where exactly do they fall into the definition trap? Think back to our 4-step framework. What are they missing between the heat going in and the current flowing out? And time is up. Let's reveal the correction. So the flawed answer completely missed the why. It skipped straight from thermal energy to macroscopic conduction. But the corrected top band answer connects the repeating order to carrier transport. It really should say, thermal energy provides enough energy to break bonds within the repeating crystal lattice, promoting electrons to the conduction band and creating free charge carriers, which then allows current to flow. Do you see the difference there? The correction physically goes inside the long-range structure, it breaks a bond, it frees a carrier, and only then lets the current flow. It completely links the crystal arrangement directly to the field response. To ensure this is deeply understood and not just blindly memorized, you need to run yourself through the 60-second recall test. Honestly, whenever you study a solid-state topic, ask yourself these 4 memory triggers out loud. Number 1, what is the idea? Repeating order and long-range structure. Number 2, what exactly changes inside the solid? That's your microscopic mechanism, like charges shifting or bonds breaking. Number 3, what can we observe outside the solid? That's your macroscopic consequence, like storing more energy or conducting heat. And number 4, where does this actually matter in technology? Connect it to real things, like turbine blades tolerating high stress, or the bonding direction in gemstones. If you can fire off these 4 answers in 60 seconds, your knowledge is totally secure. So the ultimate takeaway from this explainer is simple, but it is incredibly powerful. Stop memorizing labels. The red pen is basically waiting for students who just drop buzzwords without any context. You need to start linking microscopic causes directly to macroscopic effects. Your goal is to see the invisible atomic structure and describe exactly how it pushes, pulls, or shifts to actually change the real world. So how will you apply this 4-step framework to your next past paper? Next time you see a question about a material's properties, I want you to literally close your eyes, picture that crystal lattice, and write the discipline prose that guarantees you the top grade. Keep learning, keep visualizing, and as always, stay curious.